So, as you're preparing for your Unit 3 test and you have finished with homework number 7, the solutions homework, here's a little review of some things that I saw as I was reviewing your homework. And the first error that I noticed is you need to remember this rule with solutions that like dissolves like. And so what are we talking about here? We're talking about polar compounds. So if we have a polar solute, it's likely to dissolve in an ionic or polar solvent, like water being so polar, and that's why it dissolves so many various solutes. If you have a nonpolar solute, it's likely to dissolve in a nonpolar solvent. Polar and nonpolar, solute and solvent, typically don't mix. They're what we would call immiscible. So one of the questions on the homework was dealing with this chemical right here. This is actually methanol, and trying to figure out what would be likely to dissolve in it. So the first thing I have to do is figure out the polarity of this. And so starting with the valence electrons, 4 from carbon, 4 from the 4 hydrogens, and 6 from oxygen, determining my central atom and drawing that out and realizing, oh, oxygen is bonded directly with hydrogen. And so remembering that oxygen has an electronegativity of 3.44, whereas hydrogen is only 2.1. So, and carbon is only 2.55. So that oxygen is pulling all those shared electrons toward it, really making this little section of this molecule here have a polar sort of flavor, if you will, which is going to affect what things dissolve in it. And so, for example, you had just some carbon-hydrogen chains here. They're not likely to dissolve in that molecule because they're so nonpolar. So that was the first error. Here's another error that I noticed, a supersaturated solution. Now keep in mind that a supersaturated solution is very unstable. And so in order to make a supersaturated solution, I've taken my solution, added extra solute, and then heated it up. Then as I cool that solution down, got to be pretty careful that that extra solute doesn't precipitate out. And it can because, like I said, it's very unstable. So simply by jostling it around, if I were to put one more little tiny piece of solute in there, that would likely do it to cause precipitation in that solution. Remember that solubility in gases is the opposite of a solute. So if I have a solid solute, I heat that up to get it to dissolve. But if I have a gas, as the temperature increases, solubility decreases for gases. And so here is a graph of that, and you can see that that is exactly opposite of a solid solute in water. This is why we put soda to keep it fizzy or sparkling water in the refrigerator so that my carbon dioxide, my gas in there, don't bubble out. All right, now here's the next problem that I saw is with the colligative properties. So don't forget those colligative properties, boiling point elevation, freezing point depression, vapor pressure lowering. And so these colligative properties depend solely on the particles. So if we have these 3 ionic solutes, chemically like with the water, they'll dissolve. When I put them in the water, in the solute there, and go to dissolve them, what's going to happen is through that solvation process, the ions are going to come apart. And so we're going to get Na ions and iodide ions. And that's those ions could be right here in blue, and they affect the solution. And that's why they're colligative properties. Now, the one that's going to affect this most is going to be the one that produces the most ions floating around. And several people got this incorrect. So as you're taking a look at this, take a look at how many ions are going to be produced. And hopefully you can now see that the magnesium iodide, MgI2, is going to produce the most ions, because obviously it's going to produce 2 iodide ions and 1 magnesium ion. And so that's going to have the greatest effect on those colligative properties. So make sure that you know those. The next error that I noticed was in one like this. It said, how many moles of this, again, methanol, are in 50 milliliters of a 0.4 molar solution? And so the formula you need to use is that, there we go, molarity equals the number of moles divided by the volume. Or if I rearrange that, molarity times volume is my number of moles. And so it's simply plugging in the volume, plugging in the molarity to determine the number of moles. So pretty simple, just like that, and rounded to one significant figure, excuse me, because that's what's given in the problem. All right, now here's another one. So here was the next problem that I saw many people get incorrect. It's again a solution molarity problem, and the reason you got it incorrect was probably not your fault. It took me a while to figure this one out as well, and I will go back through and add those points to your homework for you. And the website had a mistake, and I'll show you what that is. So the balanced chemical equation was given, and you've got a 0.184 molar solution of potassium phosphate, and you've got 187 milliliters of it. So that's where you want to start to determine the number of moles. Once you figure out moles of potassium phosphate, you can determine how many moles of nickel 2 chloride are needed, the NiCl2. And so all you would need to do is take your molarity times your volume, and that's going to give you the number of moles of the K3PO4. Now, in the problem, for the correct answer, they used 2 moles of nickel chloride, and they meant 3. And they used 3 moles of K3PO4, but if you look at the balanced equation, it was 2 moles of K3PO4. So maybe if you didn't figure that out after the first time, you may have gotten the wrong answer here, and many of you did. And so, as I said, I will be correcting for that. Once you came up with the moles of nickel chloride, all you have to do is divide that by your molarity, moles divided by molarity, and that does give you your volume. And the volume there would not have actually been correct because they had set the problem up incorrectly. As you're reviewing for your test, I hope this helps you.